Magandang araw po sa ating lahat. Naimbagal daw kanya tayo amin. Good day to every one of us. Now let's discuss open delta connection of transformers. They also call this as VV connection. This system uses only two single-phase transformers to provide three-phase power supply to its loads. Unlike with the closed delta transformer banks that has three transformers, again, open delta connection uses only two single-phase transformers. And both of them can provide three-phase supply. Open delta is employed when, number one, the three-phase load is comparatively small so that the installation does not warrant a three-phase transformer bank. Example, if the computed load is 15 kVA that requires a three-phase system, obviously a 15 kVA single-phase transformer cannot be installed because the load requires a three-phase system. The lowest rating of a single-phase distribution transformer is 10 kVA. So if a closed delta transformer is used, then the capacity of the bank is 3 times 10 kVA, that's 30 kVA, which is too much for a 15 kVA load. That's why for this load, open delta system is used. But of course, the capacity of an open delta will not be 2/3 of that of a closed delta system. We will discuss that later. Let's go to the next application of open delta. It is employed when one of the transformers in a delta-delta bank fails, so that service may be continued until the faulty transformer is repaired or a good one is substituted. So it is very clear from what we've just read, open delta connection are used in emergency conditions. At least the service is continued despite one of the transformers failing. And number 3, open delta is employed when it is anticipated that the future load will increase to warrant the closing of the open delta at some time later. Again, it's clear that when expansion is needed for future loads and there's a need for a closed delta system, then open delta is used for the meantime. The total load that can be carried by an open delta transformer bank is not 2/3 of the capacity of a closed delta connection. For example, if each transformer is rated 25 kVA, at closed delta, the capacity of the bank will give us 3 times 25 kVA, that is 75 kVA. But if open delta is used, then the capacity is not 2 times 25 kVA. It will not give us 50 kVA capacity. The efficiency of an open delta connection is lower compared with a closed delta connection, because the transformers will be operating at a different condition. At full load, both transformers will operate at rated capacity, but their efficiency will be lower since their losses will be at full load losses, so their output will be reduced. But of course, we could still use open delta but at a reduced efficiency. It will tend to cause the transformers to increase in temperature compared when used in closed delta connection. To compute for the capacity of open delta connection, one way is to multiply the rating of one transformer by square root of 3. So that is, square root of 3 multiply that by the rating of one transformer. Example, if each transformer is rated 10 kVA, so we have square root of 3 times 10 kVA, this will give us 17.321 kVA. This will be the capacity of the whole open delta system. It will not be 20 kVA. Again, there is a reduction in their capacity. Another way is by multiplying the rating of its equivalent closed delta system by 0.577. From our example, if each transformer is rated 10 kVA, so therefore its equivalent closed delta system will be 3 times 10, that is 30 kVA. So we multiply that by 0.577. 0.577 times 30 kVA, that is 17.31 kVA, which is near from the value that we have computed above. Still, another way is to divide the rating of the closed delta system by square root of 3. So again, if the rating of the closed delta system is 30 kVA, divide that by square root of 3, this will give us 17.321 kVA. The 0.577 in this equation is taken from 1 over square root of 3. That's why the capacity of the open delta is 57.7%, or that is 58% of the capacity of a closed delta system. Let's have another example. What if we have an open delta system that uses two transformers, each having 50 kVA rating? Substitute 50 kVA to this equation. We have square root of 3 times 50 kVA. This will give us 86.603 kVA. If we multiply 0.577 to the rating of the closed delta system, where we have 3 times 50 kVA, that will give us 150 kVA. Multiply that by 0.577, this will give us 86.55 kVA. If we divide the equivalent closed delta system by square root of 3, 150 kVA, divide this by square root of 3, this will give us 86.603 kVA. Whatever solution we use, we should arrive at exactly or nearly equal values. Another reason for this reduction in the ratings of the system comes because the average power factor at which the two transformers will operate is less than the load's power factor. Again, if each transformer of an open delta is rated 50 kVA, and we know that the system will give us 86.603 kVA from square root of 3 times 50 kVA, to determine the kVA load of each transformer, we divide this value by 2. So that is 86.603 kVA divided by 2, we have 43.302 kVA. To determine the percentage of this load from its rating, we have 43.302 kVA, divide this by 50 kVA times 100%, we have 86.604%. That's why it says the average power factor is always 86.6% of the balance load power factor. Another example, if each transformer in an open delta system is rated 25 kVA, its open delta capacity is square root of 3 times 25 kVA will result in 43.301 kVA. Divide this by 2 to determine the kVA load of each transformer, we have 21.651 kVA. And divide this value by 25 kVA times 100%, we still have 86.604%. Another thing, except for a balanced load having a unity power factor, the two transformers in an open delta system will operate at different power factors. Again, the open delta system will operate at 86.6% of the balanced load power factor, and each transformers will also operate at different power factors. When an open delta transformer bank delivers a balanced three-phase load whose power factor is cosine theta, one of the units will operate at a power factor of the cosine of the quantity 30 degrees minus theta, while the power factor of the other unit will be the cosine of the quantity 30 degrees plus theta. The 30 degrees in these equations comes from the inverse cosine of 0.866 or the inverse cosine of 86.6%. The angle theta here is the power factor angle of the load. Therefore, the power factor of the load and the power factor at which the transformers are reduced from their capacities has an effect to the system. From these power factors of each transformers, we can determine the effective powers that can be delivered by each transformers in an open delta system. Please do not memorize these equations. They only came from power factor is equal to the ratio between the real power and the apparent power. Deriving that equation to determine the real power, we have real power equals apparent power, multiply that by the power factor. Just understand and remember the principles behind these equations. And now let's go to several simple problems. Let's go to problem number 1. Two transformers are connected in open delta and deliver a balanced three-phase load of 245 kilowatts at 460 volts and a power factor of 0.707. Calculate letter A, the secondary line current, letter B, the kVA load on each transformer, letter C, the power delivered by the individual transformers, and letter D, if a third transformer having the same rating as each of the other is added to form a delta bank, what total load can be handled? Understanding the problem is more important than solving the problem because, again, we cannot solve the problem properly if we cannot understand the problem. We have two transformers connected in open delta, and they deliver a balanced three-phase load of 245 kilowatts at a voltage of 460, having a power factor of 0.707. Letter A, we need to calculate for the secondary line current, that is IS. In order to solve the secondary line current, since we have a 245 kilowatts given, that is a real power, therefore from the formula of real or effective power, we have square root of 3 times current times voltage, multiply that by the power factor, cross multiply square root of 3 voltage and power factor to the other side of the equation. We have current is equal to real power or effective power divided by square root of 3 voltage and also the power factor. The effective power that is being delivered by this open delta transformer bank is 245 kilowatts. The voltage is 460 volts and the power factor is 0.707. Substituting those values, we have 245,000 watts. Divide this by square root of 3, 460 volts and 0.707. We have the secondary line current is 434.939 amperes. Now let's go to letter B, the kVA load on each transformer. We are looking for the apparent power, therefore, we use this formula, current times voltage. Current equals 434.939 amperes and the voltage is 460 volts. Substitute those values. We have 434.939 amperes times 460 volts. The answer is 200,071.94 volt ampere, or this is 200 kilovolt amperes. Now that we have the answers for letter A and letter B, let's go to letter C. The power delivered by the individual transformers. So that is the effective power being delivered by each transformer. To solve that, we have these formulas. The kVA on each transformer are the same, that is 200 kVA. But the power factor to which they will operate are different. Again, these formulas are being derived from the formula of the real power, which is equal to the apparent power times power factor. But anyway, before we can compute for the real power being delivered by each transformer, we first need to determine their power factors. To do that, we have these formulas. And also we need to determine the power factor angle of the load. To determine theta, we have the inverse cosine of the power factor. The power factor of the load is 0.707. Substitute that value, we have the inverse cosine of 0.707. This is 45 degrees. Now that we have the power factor angle of the load, we substitute that to these equations. For the power factor of transformer 1, we have the cosine of the quantity of 30 degrees minus 45 degrees. This is 0.966. For the power factor of transformer number 2, we have cosine of the quantity 30 degrees plus 45 degrees, that is 0.259. Now that we have the power factors, we substitute them to these formulas. For the effective power of transformer number 1, we have 200 kVA times 0.966, that is 193.2 kilowatts. For transformer number 2, we have 200 kVA times 0.259. This is 51.8 kilowatts. If we want to check if the effective power we solve are correct, we add them and see if their total is the same as the effective power consumed by the load. That is, the total power equals 193.2 kilowatts plus 51.8 kilowatts. It is 245 kilowatts, which is the same from the given in the problem. For letter D, if a third transformer having the same rating as each of the other is added to form a delta bank, what total load can be handled? Each transformer has a rating of 200 kVA. Therefore, we multiply that by 3. That is 3 times 200 kVA. This is 600 kVA. So these are our answers to A, B, C, and D. Let's proceed to problem number 2. Two transformers are connected in open delta and deliver a balanced three-phase load of 150 kilowatts at 230 volts and a power factor of 0.82. Calculate letter A, the secondary line current, letter B, the kVA load on each transformer, and letter C, the power delivered by the individual transformers. Again, it is very important to solve similar problems so that we would be familiarized. And in that way, we could easily understand and remember how to solve this kind of problems. So we have an open delta system delivering a balanced load of 150 kilowatts at a voltage of 230, and its power factor is 0.82. Letter A, determine the secondary line current. Again, from the formula of the real power or effective power, we have square root of 3 times current times voltage times power factor. Cross multiply the square root of 3, the voltage and the power factor, to the other side of the equation to determine the current. We have real power divided by square root of 3 voltage and power factor. Substitute the given values. 150 kilowatts, or that is 150,000 watts, divide this by square root of 3, divided by 230 volts, and also divide this by 0.82. We have 459.186 amperes. For letter B, calculate the kVA load on each transformer. A simple formula, that is current times voltage. We already solved for the current, and the voltage is 230 volts. Substitute those values. We have 459.186 amperes times 230 volts. The answer is 105,612.854 volt amperes, or this is 105.6 kVA. Now let's go to letter C, the power delivered by the individual transformers. To determine that, we use this formula. Again, this is just simple apparent power times power factor. But of course, we first need to determine the power factor of each transformers. So these are the formulas that we are going to use. And of course, we need to determine first the power factor angle of the load. Using this formula, the power factor of the load, that is 0.82, substitute that. So therefore, theta equals the inverse cosine of 0.82. Theta is equal to 34.915 degrees. Now that we have this value, substitute them to these two equations. For the power factor of transformer number 1, that is cosine of the quantity of 30 degrees minus 34.915 degrees, the answer is 0.996. For the power factor of transformer number 2, that is the cosine of the quantity of 30 degrees plus 34.915 degrees, this is 0.424. And now that we have the power factor of each transformer, let's solve for the power delivered by each of the transformers. For the power delivered by transformer number 1, that is 105.6 kVA times 0.996. This is 105.178 kilowatts. For the effective power delivered by transformer number 2, that is 105.6 kVA times 0.424. This is 44.774 kilowatts. If we want to check whether our answers are correct, let's add them up, and they should be equal to 150 kilowatts. So 105.178 kilowatts plus 44.774 kilowatts, this is 149.952 kilowatts, which could be rounded off to 150 kilowatts. Now let's proceed to problem number 3. Two transformers are connected in open delta and deliver a load of 86.7 kVA at a power factor of 0.8. Calculate, letter A, the kilovolt ampere load on each transformer. Letter B, the power delivered by each of the two transformers. Letter C, the available transformer kilovolt ampere if a third unit of the same rating as one of the other two is added to form a delta bank. Again, we have an open delta system. It delivers 86.7 kVA at a power factor of 0.8 to a load. Letter A, we need to calculate for the kilovolt ampere load on each transformer. To do that, we could divide the total kVA delivered to the load by square root of 3. So 86.7 kVA divided by square root of 3, the answer is 50.056 kVA. Or another way is to multiply 0.577 to the total kVA delivered to the load, that is 0.577 times 86.7 kVA, the answer is 50.026 kVA. Since 1 over square root of 3 is equal to 0.577. But of course, we can round off our answer to 50 kVA. So the kilovolt ampere load on each transformer is 50 kVA. Now for letter B, calculate the power delivered by each of the two transformers. Again, we use these equations. We already have the kVA of each transformer, that is 50 kVA. let's compute for the individual power factor of each transformer. To do that, we have these equations, but of course, we need to first determine the power factor angle of the load. So theta equals the inverse cosine of the power factor of the load. Substitute 0.8, that is the inverse cosine of 0.8, theta equals 36.87 degrees. Now that we have the power factor angle of the load, we can determine the power factor of each of the transformers. For transformer number 1, the power factor equals the cosine of the quantity 30 degrees minus 36.87 degrees. This is 0.993. And for the power factor of transformer number 2, we have the cosine of the quantity 30 degrees plus 36.87 degrees. We have 0.393. Now we can determine the effective power delivered by each of the transformer. For transformer number 1, that is 50 kVA times 0.993, the answer is 49.65 kilowatts. For transformer number 2, 50 kVA times 0.393, the answer is 19.65 kilowatts. And now for letter C, calculate the available transformer kilovolt ampere if a third unit of the same rating as one of the other two is added to form a delta bank. That is simply multiplying the rating of each transformer, that is 50 kVA, by 3. So 3 times 50 kVA, that is 150 kVA. Now we have problem number 4. An open delta bank delivers a balanced 3-phase load of 60 kVA at 460 volts. Letter A, what current flows in the secondary of each transformer? And letter B, what kilovolt ampere load does each transformer carry? So that is an open delta bank. Its load is 60 kVA at 460 volts. For letter A, let's determine the secondary current of each of the transformer. From the formula of the apparent power in three-phase system, that is square root of 3 times current times voltage, cross multiply square root of 3 and voltage to the other side of the equation, we have current is equal to the apparent power divided by square root of 3 and divide that also by the voltage. Substitute the given values. We have 60 kVA divided by square root of 3 and 460 volts, that is 75.307 amperes. So this is the current that flows in the secondary of each transformer. Now let's go to letter B, the kVA load of each transformer. That is simply current times voltage because we are solving for the kVA load of each transformer. Current equals 75.307 amperes and the voltage is 460 volts. But of course, we need to convert that into kVA. So we have 75.307 amperes times 460 volts times 1 kVA is 1000 volt amperes. The answer is 34.641 kVA. Last problem, number 5. An open delta bank delivers a balanced three-phase load of 40 kVA at 230 volts. Letter A, what current flows in the secondary of each transformer? And letter B, what kilovolt ampere load does each transformer carry? This is similar to problem number 4. So the load of the open delta is 40 kVA and its voltage is 230 volts. To determine the current that flows in the secondary of each transformer from the formula of the apparent power at three-phase system, cross multiply square root of 3 and voltage to the other side of the equation, we have current equals apparent power divided by square root of 3, divide that also by voltage. Substitute the values. We have 40 kVA divided by square root of 3 and 230 volts. The answer is 100.409 amperes. For letter B, kilovolt ampere load of each transformer. Again, since we are solving for the kVA load of each transformer, we use this formula. But since we are asked to determine its kVA load, therefore we multiply that by 1 kVA divided by 1000 volt amperes. Substitute the values. Current equals 100.409 amperes and the voltage is 230 volts. Multiply that by 1 kVA, divide that by 1000 volt amperes. The answer is 23.094 kVA. Hopefully, we learned something today. Thank you so much for watching. Please like, share, and subscribe. Magandang araw po sa ating lahat. Na imbagal daw kanya tayo amin. Good day to every one of us.